Hello friends, let us resume our discussion on grinding. So if you could recollect, this entire discussion on the process of combination began with a process chain. Now when one considers just the process chain alone, it is rather straightforward to distinguish different events that occur in this process chain into two. So one is crushing, the other is grinding. Now while introducing the crushing, we consider the distinguishing features, how grinding is different from that of the crushing. Now the process chain itself helps us differentiate grinding from the crushing. So one distinguishing feature that is evident in the process chain alone is that the grinding occurs in different stages, or rather crushing occurs in different stages, whereas the grinding often is completed in a single stage. So the grinding is achieved rather in a single stage. So the grinding is rather a more straightforward process when compared to that of the crushing. So in case of crushing, we saw that the feed that you provide in for the different crushers that are involved are quite different. For instance, depending on the position of the crushing, we categorize these different crushing processes into primary, secondary and the tertiary. So again, if you could recollect the process chain, the initial crushing was referred to as the primary crushing and the subsequent crushings were referred to as secondary and tertiary respectively. Now, in the primary crushings, we saw that there is a unique form of equipment that is involved when compared to that of the secondary and tertiary crushing. The reason for employing this unique form of equipment is primarily because the feed that you provide is considerably larger than the feed that you provide for the subsequent crushings and also grinding. In primary crushing, you would be feeding in the run-of-mine particles which are of the order of meters, and therefore essentially the machinery that you use should be able to accommodate such large sized feed, and correspondingly at the end of the primary crushing, the output we get is in the order of centimeter, and therefore what we are essentially doing in primary crushing is significantly reducing the size of the particles. So therefore in primary crushings, heavy duty machineries are involved, and not so heavy duty machineries are involved in the subsequent stages including grinding. So this consideration alone helps us distinguish sufficiently crushing from grinding. One, the process chain helps us understand that crushing is a different stage process, whereas mostly grinding is a single stage one. And correspondingly, and also in case of within the crushing itself, there is a different equipments that are involved depending on the stages of crushing. In case of the primary crushing, we involve heavy duty equipment, and also heavy duty equipments are involved in secondary and the tertiary crushing. So these are few differences that one could gain just by considering the process chain and the equipments that are involved. In addition to that, just by focusing on the machineries that we employ, there is also a distinguishing feature that is associated between, that differentiate crushing from grinding. So from the process chain and considering the input and output, one can distinguish crushing from grinding. Now from the point of view of the machineries that are involved, the equipments that are involved, there is also a striking difference between crushing and grinding. So if you could recollect, the equipments that are involved for crushing can all be related to that of the primary crusher, which is the jaw crusher. So for different stages of crushing, of course we use different equipments. Nevertheless, despite the difference in the equipment, the mode of operation, owing to the similarity in the mode of operation, the crushers that are involved in the secondary and tertiary stages, the crushers that are commonly involved in the secondary and tertiary stages, can be related to that of the primary crushers. Of course, there are differences, or rather, of course, there are exceptions like the roll crusher and also the impact crusher. Nevertheless, when you consider the crushers that are mostly involved in the secondary and the tertiary crushing, we see that the scone and the gyratory crusher, which are involved in the crushing process, can be related to that of the jaw crusher. So the reason we are able to relate it to that of the jaw crusher is because the operation through which the fragmentation is achieved is rather similar. In case of jaw crusher, what you have is a immovable jaw and a jaw that exhibits a restricted movement. So the similar operation is observed in both gyratory and also in the cone crusher. in gyratory and also in the cone crusher, you have one component that exhibits a restricted movement and the other component that is rather relatively immobile. So combination of these components, the combinatory operation of these components ultimately lead to the fragmentation of our input particles. Now, when compared to this principal operation of the crushers, in case of grinding, the operation is quite different. Again, the operation in case of grinding depends not on the relative movement of its components, but rather the movement of what is referred to as the grinding media. So this is something we saw in our previous lecture. So this grinding media is nothing but a component, a smaller component that are fed along with the mineral particles into the grinding mill. So grinding is usually executed in a grinding mill, and when you feed in your input particles or input particles or input mineral particles, you along with it you include this grinding media, and this grinding media, they can be rods or spherical balls, and these rods and spherical balls are made up of, or usually they are made of, hard wear resistant material. Often hard wear resistant alloys or hard and wear resistant ceramics. The reason we need to have these specific properties associated with the grinding media is that the life of the grinding media through this combination of properties will be enhanced. If the grinding media is not made of such hard and wear resistant particles, then the life of the grinding media will be sufficiently reduced. So therefore, there are unique combinations of property that are required to build this grinding media, and the primary properties that needs to be associated with the grinding media is these grinding media should be hard and also they should be wear resistant. Now we saw in the previous lecture that the grinding mill it is rather developed in two ways. One is an horizontal grinding mill and other is a stir grinding mill. So in case of the horizontal grinding mill, which is shown in this figure here, what you have is an external shell, and internally this shell is surrounded by trunnions, and this shell here that is visible to us, the shell here is rotated, and during this rotation the grinding media that is fed into this mill along with the input particles, they interact and ultimately lead to the fragmentation of the particle. So this is rather the straightforward, or this is how the fragmentation is achieved in grinding, and understanding is rather straightforward. Now when you consider the operation of the grinding mill, be it, so far we have considered the operation of the horizontal grinding mill, and if you compare it to that of the operation of crushing, we observe that while in the crushing it is possible for us to rather definitively state the response or the behavior of the material, behavior of our input material within the crushers. In case of the grinding mill, what we are able to state is the probability of the fragmentation. In case of the crushing, it is possible for us to definitively state that as the input feed passes through the crushers, the load that this input feed experiences, it increases as it moves down the crusher. However, such reductions or such description cannot be associated with the operation of the grinding mill. In case of the grinding mill, the fragmentation is largely associated with probability, and it is often referred to as a random act. And even though we are able to express the way the fragmentation is achieved or describe the way in which the fragmentation is achieved in the grinding mill, we are able to rather enumerate the different forces that allow us to achieve fragmentation during grinding. We cannot definitively state which of this process brings about how much amount of fragmentation, and therefore it is all a probability reduction. So it is all, we can state that probably this particular force brings about the large amount of fragmentation when compared to the other forces that are involved. So this is one key contrasting feature that distinguishes crushing from grinding. In case of crushing, you can definitively state that as the input feed goes through the crushers, there is a specific amount of the force that is experienced by the feed, and there is a specific size reduction achieved at each of these stages. However, in case of grinding, there are several different forces that act on our input feed, and the amount of fragmentation rather achieved by each of these forces can be stated based on a probability alone. Now, this is one of the differences that one could observe while studying the operation of the grinding and that of the crushing, particularly while studying how the fragmentation is achieved during grinding and compared it with the fragmentation that is achieved during crushing. Now, despite being largely a random process, despite the probability being involved in order to achieve or in order to understand how much of the fragmentation is achieved during, or how much of the fragmentation is achieved through a particular force during grinding, we are able to rather describe how or what are the different ways the crushing or the comminution can be achieved through grinding. So what is largely the governing principle that rather dictates the fragmentation during grinding? So this we saw at the end of the previous lecture. So even though grinding largely is, when compared to that of the crushing, is a random process, and even though there is a significant role of probability that is involved when we consider the exact force that brings about the fragmentation, it is possible for us to describe how the fragmentation is achieved during the grinding process. Now again, this grinding process, or the way in which the fragmentation is achieved through this grinding process, is restricted to that of the horizontal mill. So the operation that we see, the methodology that we see, how the fragmentation is achieved, is restricted to that of the horizontal mill. So as we see that the horizontal mill, it comprises of two components, that is the shell and that is the external component or the external surface, and in the inner surface we have the tronions. And what do you essentially see here? The circular ring that is in dark black or thick dark black is the tronions. And essentially what you have is, in case of the horizontal mill, you have the rotation of the shell, and as the shell rotates, you have the combination of your grinding media and also your feed. And in response to this rotation, this grinding media and the feed that is fed into the grinding mill, the horizontal grinding mill, they begin to rotate. And the way the fragmentation is achieved through this rotation we saw in our previous lecture. So essentially what we have is, in response to this rotation, the combination of the mineral feed and the grinding media, they begin to rotate and get carried away along with the rotation, and after they reach a dynamic equilibrium, they begin to fall onto the tronion. So you have the movement that is in keeping with the rotation of your grinding mill, and after reaching a dynamic equilibrium, the combination of grinding media and feed begins to fall, and they do not fall directly onto the tronion. They do not directly hit onto the tronion, but they hit on the portion of the feed, and this portion of the feed that the falling combination of grinding media and feed hits is what we refer to as toe. So you have a shoulder where the dynamic equilibrium is achieved, and above the shoulder you have the falling of the grinding media and the feed. The grinding media and the feed, they do not fall or hit directly on the tronion, but they hit on the portion of your feed that comprises of the mineral particles, and this portion on which they hit, it refers to as the toe. And here the forces that are involved is, the primary force that is involved when the combination of grinding media and feed falls on the toe is impact, or rather an instantaneous compressive force. And because of this instantaneous compressive force, what essentially happens is you would have a transfer in energy and ultimate fragmentation of your particles. So essentially, in case of toe, the fragmentation is achieved through the impact between the falling combination of the grinding media and the feed and the particles that are present in the toe. So a large portion of the fragmentation during grinding in the horizontal mill is achieved by the instantaneous compressive load or impact loading, and this occurs at the toe of your input feed. The toe is indicated here, and this occurs at the toe of the input feed. And in the previous lecture we saw that there is another form of the force that also brings about the fragmentation, and this is observed in this abrasion zone. In this abrasion zone, you observe another form of interaction that brings about the fragmentation, and this interaction is not between, or is not primarily between, the grinding media and the feed, but this interaction is primarily between the mineral particles themselves. And this interaction is because of the cascading movement of the particle. So what we mean by cascading movement is, the cascading movement can be rather visualized when you consider, like we saw in the, like we discussed in the previous lecture, it can be rather imagined like they are related to that of the flow of the water when you pour it from the top of your steps, and as the water flows down your steps on the staircase, the way the water flows down is what we refer to as the, or it is what we can relate it to the cascading movement. So essentially what you have is the layers of the feed and the grinding media that are on the trunnion. They move along the direction of the rotation of the shell. So you have a specific direction along which this shell rotates, which is indicated here, and the layer of the feed that is on the surface of the trunnion, it moves along the direction of rotation. However, the layers that are above the surface of the trunnions are the particles at the surface of the trunnions. So these layers that are above the particles that touch the surface of the trunnions, they exhibit a cascading movement in the opposite direction, and because of this cascading movement in the opposite direction, there is an interaction between the mineral particles themselves and the mineral particles and the grinding media, and this interaction is largely abrasive in nature, and this brings about the further fragmentation. So essentially it is the cascading movement, and this cascading movement brings about an abrasive force, and this abrasive force ultimately lead to further fragmentation. Now the fragmentation that you observe during the grinding process is largely due to the combination of these two mechanical forces. One, the impact loading or instantaneous compressive loading, and the other is the abrasion. And also there is a third one, that is chipping, and again it has to do with the interaction between the particles largely, and they also play a vital role, but it is not as much as the role played by the impact and the abrasion loading. So essentially this is how the grinding brings about the comminution, or it brings about the fragmentation of these particles. Now when you consider this particular operation, which again we have seen in the previous lecture, when you consider this particular operation of the grinding mill, it is important to note that there are two factors that largely govern the operation, or they largely govern the efficiency of the grinding mill. Now that we have understood how the fragmentation is achieved, so the primary factors that brings about the fragmentation during the operation of the grinding mill, there are two critical factors that govern the efficient fragmentation within the grinding mill, particularly the horizontal grinding mill. One is the diameter of your shell, or the diameter of the horizontal grinding mill, and the other is the speed with which the grinding mill rotates. So these are the operating factors that govern the amount of fragmentation, the efficiency of comminution that is achieved during grinding. Now it is possible for us to consider or imagine how the diameter would influence the fragmentation that is achieved during grinding. So primarily the diameter, it influences the fall of the particles from or during the grinding process or the comminution process. So the degree of fall of the particle from the shoulder to toe, it is largely governed by diameter. So greater the diameter, so greater is the degree of fall, and the larger would be the impact load that is influenced or that is observed at the toe region. So when you have a mill of a quite large diameter, it means that when the combination of grinding media and the feed falls from shoulder to toe, the amount of impact that is experienced at the toe will be higher. So the amount of impact that brings about the fragmentation in the toe region will increase as you increase the diameter. However, beyond certain diameter, when you, in order to just achieve the increased amount of impact loading, when we build our horizontal grinding mill with a huge diameter, then it becomes difficult for us to appropriately place this equipment in a given industrial setup. So therefore, the diameter, even though with increase in it, brings about or increases the amount of impact load at the toe, the enormity of the largeness of the equipments make it impossible or rather difficult for us to devise it or place it in an industrial setting. So therefore, a trade-off, therefore a decision must be made on the efficient compromise between the building of an horizontal mill and also bringing about the sufficient degree of impact load at the toe. So therefore, addition must be made, addition must be arrived at by considering both these impact loading that needs to be achieved and also the construction of this horizontal mill. When your horizontal mill is smaller, on the other hand, when your horizontal mill is smaller, when the diameter of your shell is smaller, then you will not be able to achieve sufficient impact loading in order to bring about the combination. So therefore, there needs to be an addition made, an optimal decision made to ensure that the sufficient amount of impact load is achieved, and secondly, the equipment itself does not occupy unnecessary space or it is not too large. So the diameter primarily influences the amount of impact load that is imposed at the toe, and so considering that in case of grinding, particularly in horizontal mill, the impact load plays a primary role in bringing about the combination. The diameter then plays a vital role. The diameter of your mill plays a vital role in determining the degree of combination. Again, in case of, we have now seen the operation, or we are now familiar with the operation of the grinding mill, how the fragmentation is achieved in the horizontal grinding mill. One key feature that brings about the fragmentation is the impact loading that is arrived at when the feed and the grinding media falls from the shoulder to toe. This fall from the shoulder to toe, it depends on the diameter of your mill. And as you increase the diameter of the mill, rather, what you essentially will be doing from the perspective of the operation is you will be increasing the fall, thereby increasing the impact loading. And greater the impact loading, the greater will be the fragmentation. However, we cannot keep on increasing the diameter because that will hamper the size of the overall size of the mill. So therefore, a balance needs to be arrived, or a balance needs to be reached. Now, in case of speed, now it is possible when your the overall mill is rotating at the higher speed, because of the associated centrifugal force, the fall is rather avoided. It is possible for us to avoid the overall fall by increasing the speed of the rotating mill. So again, the speed should be appropriately devised in such a way that we allow for the sufficient, or we allow for the falling of the input particles and the grinding media from the shoulder to toe. So like diameter, the speed with which we are rotating the mill also plays a key role. The first role is the speed plays is by ensuring that there is a shoulder and there is a toe. When you increase the speed to such, it is possible for us to increase the speed to such an extent that the amount of fall that you experience is too low. The amount of fall you experience is rather marginal. It is possible for us to increase the speed in such a way that all the particles stick onto the surface of the trunnion because of its increased speed, because of the centrifugal force. So therefore, the speed should ensure that there is a fall that is introduced. So first thing, the speed should ensure that there is a fall that is introduced within the grinding mill. The speed should not be high in order to introduce the centrifugal force that enables the particles and the grinding media to stick within stick to the surface of the trunnion. So the speed should be appropriately devised in order to ensure that there is a fall of the grinding media and the feed. So it is this fall that primarily brings about the fragmentation. So therefore, the speed should be appropriately introduced in order to ensure that there is a fall of the grinding media and the feed. And secondly, the speed should be sufficient enough, or it should be low enough so that the fall of the grinding media and the feed does not directly hit the trunnion, but it hits the toe. It hits the portion of your feed, the portion of your mineral particle. So essentially, one purpose of regulating the speed is that it should ensure the fall of your grinding media and the mineral particle. And secondly, the speed should be sufficiently regulated in such a way that the fall does not directly hit the surface of the trunnion, but rather it hits the toe of your input feed. So the probability of this fall hitting the toe of your input feed, it depends on the speed with which the grinding mill is rotating. So therefore, when the diameter is fixed, the speed should be appropriately regulated to ensure that the fall from the shoulder should hit the toe, not the trunnions directly. So the speed is appropriately devised so that the fall hits the toe. So the interaction between the fall the interaction between the falling particles and the particles at the toe is ensured. The interaction between particles that are falling from the shoulder and the toe is ensured. So this is ensured for a fixed diameter. This is ensured by speed, and also the speed ensures the interaction between the mineral particles. So we saw that the way fragmentation is achieved within an horizontal grinding mill is by largely two various interactions. One is the impact loading that is caused by the fall from the shoulder to toe, and secondly, it is the interaction between the mineral particles, largely between themselves in the abrasion zone while they exhibit a cascading movement. This cascading movement and this development of the abrasion zone is again, for a given diameter, is again related to speed. When you have increased the speed when you increase the rotating speed of your horizontal mill, what essentially happens is this abrasion zone and this cascading medium or this cascading movement gets restricted, and the interaction gets restricted. It gets reduced. However, when your speed is again too small, this interaction is not efficient to bring about fragmentation. So if you consider at high speed, there is not much interaction or the cascading movement. When you consider low speed, even though there is a cascading movement, it is not sufficient enough to bring about the fragmentation again. So therefore, there needs to be a right balance in order to ensure that there is a cascading movement, and this cascading movement brings about fragmentation. So ultimately, from the operation of, or from our understanding of how the fragmentation is achieved in the horizontal grinding mill, it is possible for us to understand that two key factors govern the fragmentation. One is the diameter. So we saw that the diameter principally influences the impact loading, the amount of impact load that is experienced by the feed. So as you increase the diameter, the amount of the impact force that is experienced increases. However, increasing the diameter ultimately increases the size of the horizontal mill. So a compromise has to be reached between the advantage of the increased impact load and the increasing size that is brought about by the increase in diameter. The other factor, the reason we consider largely the speed is primarily because once you have fixed the diameter, the one other factor that is possible for us to rather easily vary is the speed. So therefore we have considered or spent some more time than the diameter in order to understand its influence on the fragmentation of the particles within the horizontal mill. So we have two different factors that can be governed by us in order to ensure the efficient fragmentation within the grinding. So one is the diameter and other is the speed. So once you build a horizontal grinding mill, the diameter is fixed. And now what we end up with is only the other variable, that is the speed. Now by varying speed, it is possible for us to dictate the efficiency of fragmentation that is achieved within the horizontal grinding mill. So what essentially speed does is it influences the degree of fall. So when you have high speed, so the degree of fall from the shoulder to toe of the grinding media and the feed decreases. So and when you have a very low speed rotating mill, then there is not much fall from the shoulder to toe. So in order to have a sufficient fall from the shoulder to toe, the sufficient impact loading that is experienced in the toe, we need to have appropriate speed. A very high speed, there is not enough fall. A very low speed, again all that you have will be a cascading movement, not enough fall. So we need to have an optimum level of speed. Secondly, the speed ensures that whatever material that falls, whatever feed that falls from the shoulder hits the toe. So our speed must be appropriately included. Our speed of the rotation, the way or the speed with which the mill rotates should be appropriately fixed such that the feed that falls from the shoulder should hit the toe of our input, not directly the true neons. So this again is governed by the, once the diameter is fixed, this again is governed by the speed with which the mills rotate, the horizontal mills rotate. And finally, the cascading movement that is observed in most of the, or that is observed in the within the horizontal mill in a specific region, it is its effectiveness, the effectiveness of the cascading movement to bring about a sufficient degree of abrasion and sufficient fragmentation is governed by speed. When you have a mill that is rotating at unnecessarily a high speed, then there is not much cascading movement that is involved. All the particles, they will be carried away by the rotation of your mill. On the other hand, when the mill is rotating at a very low speed, even though there is a cascading movement, what essentially you will observe is that this cascading movement does not bring about sufficient abrasion in order to bring, or in order to rather introduce the required fragmentation. So this diameter and speed, by dictating impact and the amount of, or the effectiveness of abrasion, they ultimately influence the fragmentation. So we saw, or we considered the way in which the fragmentation is achieved during the operation of the grinding mill. From that, by appropriately governing the diameter of your horizontal mill and the speed at which it rotates, we will be able to appropriately, or we will be able to introduce the required impact load and the required abrasion to bring about the desired fragmentation. So once the horizontal mill is built, the key factor, so once an horizontal mill is built, meaning the diameter is fixed, the key factors that ensures the desired degree of fragmentation in the horizontal mill is the speed at which it rotates, and through the speed at which it rotates, we will be able to ensure that there is the sufficient form of loads that are imposed in order to achieve the desired fragmentation. Now, all these discussions have largely been confined to that of the horizontal mill. Now, one other form of the grinding process that is industrially being employed is referred to as the stir milling or stir grinding. So, you have the horizontal mill and you have this stir mill. Now, the horizontal mill is also referred to as the tumble mill, and the process that is involved or the way in which the fragmentation is achieved in the tumble mill is referred to as the tumble grinding. So essentially what you have is, in case of the horizontal mill, you have tumbling of particles, you have tumbling of the grinding media and the mineral particles. So therefore, because of its operation, because of the way in which the fragmentation is achieved in the horizontal mill, it is also referred to as the tumble mill. Now, as opposed to this tumble mill, this horizontal grinding mill, what we have is, we have a stir grinding mill. So the stir grinding mill, in contrast to that of the tumble mill, which is built in an horizontal fashion, the stir grinding mill is, as you can see here, it is rather developed in a vertical manner. It is rather positioned in a vertical manner. And as the name indicates, in case of the tumble mill, what you essentially have is, you have the interaction between the grinding media and the mineral particle, largely because of the tumbling event that brings about the fragmentation. However, in case of the stir mill or the stir grinding mill, instead of introducing a tumbling, you stir the combination of the grinding media and the mineral feed. So in case of both tumble mill and the stir mill, the input feed remains the same. In both tumble mill and in the stir mill, the input feed is the grinding media and the mineral feed. However, in case of the tumble mill, the way the fragmentation is achieved is quite different from the way the fragmentation is achieved in the stir mill. In case of the stir mill, what you essentially have is, you have stirrers like this, the one highlighted in red. So you have the stirrers like this. So this stirrers, they introduce a specific form of interaction between the grinding media and the mineral. So when you compare, or when you consider the forms of load that brings about the fragmentation in the tumble mill, we saw it is the combination of the impact loading and the abrasion. So in case of the tumble mill, it is the combination of impact loading and abrasion. However, in case of the stir mill, we do not have any fall, or we do not have an introduction of a shoulder or a toe. So that means the role of impact loading is rather limited. So in case of stir grinding, in case of in the stir mill, the role of impact loading is rather limited, and the fragmentation in the stir grinding is largely brought about by the interaction between the grinding media and the mineral themselves. So therefore, one distinguishing features, of course, just by considering the build of the stir grinding or the stir mill and the tumble mill, it is possible to say that one is rather horizontally built and one is vertically mounted. In addition to that, we saw that in case of the tumble mill, it is the tumbling process of the grinding media and mineral that brings about the fragmentation. In case of stir grinding, it is the movement of the stirrer that brings about the interaction, and this interaction is largely responsible for the fragmentation. So these are two key differences that one can understand, or that one can conceive just by considering the way these two mills are built. However, when you look closely, in case of the operation of a tumbling mill, the way the fragmentation is achieved in a tumbling mill, it is largely due to the impact loading that is brought about by the fall of the grinding media and the mineral from the shoulder to toe, and such fall is not observed in the stir grinding. And in stir grinding, the fragmentation is largely due to the interaction between the mineral particles and the grinding media, and mineral particles themselves. So essentially, the role of impact loading in grinding through the stir mill is largely reduced. It's significantly reduced when compared to that of the tumble mill. And here, the fragmentation is achieved. In case of stir milling, the fragmentation is achieved So in case of stir grinding, the fragmentation is achieved through abrasion and through chipping. So in stir grinding, the communication is largely achieved by the interaction between the input feed, and this interaction largely comprises of abrasion and chipping. Now if you consider the way the fragmentation is brought about within the a stir mill is that you have a stirrer and you feed in your input, and this stirrer begins to rotate, and this rotation of the stirrer, it brings about the interaction between the grinding media and the mineral particles, and mineral particles themselves, and this interaction involves abrasion and chipping, and because of this interaction, what you essentially would have is you would end up fragmenting the input mineral particles. And this essentially will, if you consider, what will happen is, even though initially your feed will settle down at the bottom of your equipment, and as the rotation progresses, the amount of interaction increases, and correspondingly the fragmentation increases, the size of the particles or the size of the mineral particles decreases. What essentially would happen is, you see these white windows here. In these white windows, let me highlight it in red. So in these white windows, so these white windows, they comprise of apertures. So these white windows would comprise of apertures, and through these apertures the fragmented particles will pass through and they get collected here. So what essentially happens is, when you feed in your input particles along with the grinding media, they reach the stirrer in the initial stage, and the interaction begins between the mineral particles and the grinding media. So you initially feed in the combination of the grinding media and the mineral particles, and because of their size and weight, they reach the bottom of this mill, where it is acted upon by the revolving stirrers. And when they are acted upon, they interact with each other, they impose the abrasion and chipping, they experience chipping and abrasion. Because of this chipping and abrasion, they begin to fragment. The size of these particles begins to reduce, and as the size of the particles begins to reduce, and because of the stirring movement, the particles that have sufficiently reduced their sizes, they begin to float and reach this white window here, which is referred to as the media retention screen. So in few moments we will see why it is referred to as the media retention scheme. Nevertheless, it reaches the white window here after achieving sufficient degree of fragmentation, after experiencing sufficient reduction in size. These particles, they reach this white window here. This white window comprises of apertures, and in these apertures and these smaller particles, they interact, and the particles that are smaller in size when compared to the apertures, they move through this white window and they get collected here through the product launder. And this white window, it is referred to as the media retention center, because this white window will not allow the grinding media, which is relatively of larger size, to pass through, and therefore it is referred to as the grinding media or media retention screen, because even though due to the rotation of the stirrers, it is possible for the grinding media to reach this white screen or this white window. Because of the large size of the grinding media and the lower size of the apertures, these grinding media will not be allowed to pass through this screen, and therefore they are referred to as the media retention screen. So essentially here the contrasting feature is, apart from its build and the way apart from how these stir mills are being devised or they are being installed, and apart from how the additional components that are being involved in this, and how the fragmentation is achieved, when you consider the mechanical forces that are involved, the impact loading, which played a dominant role in the tumble mill, does not play much of a role in the stir mill or in case of stir grinding. So the key rules are being played by the interaction between the grinding media and the mineral particles themselves. When you consider the context, from the context of or from the viewpoint of the mechanical forces, it is the abrasion and the chipping interaction that brings about the fragmentation. And the way the fragmented particles are separated from that of the particles which are yet to experience fragmentation or it's to reach the sufficient degree of fragmentation and the grinding media is through the movement of the fragmented particles which are allowed to rise above the or which are allowed to move away from the bottom of the stir mill and reach the media retention screen. And in the media retention screen there are apertures, and through these apertures the fragmented particles are allowed to pass through, and given the size of the grinding media is larger than that of the apertures, they are retained within the mill for further fragmentation. So this is largely how the grinding or the stir mill operates, and we have seen the distinguishing features of the stir mill when compared to that of the tumbling or the horizontal mill. So with this I would like to wind this lecture up, and in the subsequent lecture we will spend a few minutes by considering one of the process that is rather implicit in the overall sequence of the comminution process. So we have seen two different large categories of techniques that are involved in comminution, and in addition to that there is a hidden technique that is associated with comminution, and that we will see in the subsequent lecture. So I hope you are able to distinguish the crushing from grinding, and even within the grinding you are able to distinguish the different techniques that are adapted and how one can differentiate the horizontal or tumble mill from that of the vertical or the stir mill. So we will see ourselves in the next lecture, wherein we will try to conclude the entire techniques that are associated with comminution. Goodbye.